So we'll try again. All right, hashing is important to authentication. Authentication is what? It is proving who you are.
Yeah.
Which then leads to what you can access. Remember our, what is that triple thing that we have? Authentication. Yeah, there's something called AAA authentication, accounting, something else, but it keeps
Authorization.
accounting authorization. So, okay, now I'm getting mixed up. Authentication means that you are identifying yourself as you to the system.
3A, yeah.
Yeah, the 3A thing. So authentication, you're identifying yourself to the system. I can't remember the second one now.
Authorization.
Authorization means that once you're authenticated,
Permission, yeah.
you have permission to post things on your Facebook profile, post YouTube videos, whatever, based on who you are. And then accounting means that they're keeping track of you. Big Brother is always there. Does that give you kind of pause? But yeah, you're being tracked. When you log into WNCC, do anything, there's logs that people can look at to see what's going on. Are there any logs here in this room to keep track of what you're doing, do you think? No. I mean, I may have logs, but I haven't set anything up. I do have, I can tell where everybody's surfing and which computer they're surfing from. That's about it. So, hashing takes plain text, grinds it up with a one-way mathematical calculation that cannot be undone. You cannot derive the original value from the hash. So the hash function scrambles this one way. So how do we use this in authentication? That's a good question. I'm glad you asked that. Well, if nobody's going to ask questions, I'll ask them myself. Well, I know in this class, everybody asks questions. All right, so let me bring up the code, which is one way to look at how this works, because the code breaks it apart into pieces. So we start out with hashing with HashLib. There are many encryption and hashing libraries. Python has one that's built in that does the normal stuff. So we are going to enter a string, right? Encode is something we may or may not have seen before, but hashing works with bytes. So normally if we have to work with something, if we're going to multiply or subtract, we convert it into a integer or float. Well, in this case, hashing works on bytes. So we have to encode this into a sequence of, no, it should say of bytes. So we're entering something into our input string. We're encoding it into bytes. That means that this input string isn't an input string anymore. It's actually input string that's now bytes. I couldn't figure out a better way to label it, but
Is that the same thing that Hashcat does on the web?
yeah, Hashcat, whatever. They all have to have bytes because on the network, when you're at the physical layer, everything is zeros and ones. You know, the data link layer down is all zeros and ones. There is no 1, 2, 3, 4. As the information goes down the network stack, it gets taken apart. And at the end, it becomes zeros and ones, whether it's wireless as the physical medium, whether it's Ethernet cables like we have for the computers in this room, or it's fiber like how we are connected down to WNCC, and that uses light pulses. But at that point, it's physical and it's all zeros and ones. So hashing works, I don't know if hashing works at the data link layer, but that's where we hash it. We hash it so that it's bytes. We take the string that's coming in at the top. What goes on the wire is a hash sequence of bytes. How about that? Because it starts out up here at the above the application layer, because the application layer of your network model is called application because that's where the application talks to your network stack. Yeah, stack's what we usually refer to it as, because we have at the bottom, we have physical, we have data link, we have IP, we have transport, which is layer 4, and then 4, 5, and 6 are kind of mushed together. So as we go down the stack and start taking apart this input string, we need to encode it into bytes right now because we need to scramble it before it goes further and goes out on the wire. And that's what happened at the application layer because hash is an application. Okay, I sorted that out for me. I don't know if that helped for you or not. All right, so we have this, we have to, before we send it out on the network, we have to encode this as bytes. So I am calling my generate hash function, right? I'm putting in my parameter or argument, comes in here as a parameter, and does this have to be the same name as this? There's a good question for you, Sean. Have we done functions? We haven't done functions in Python. So we're passing the value that's stored in this variable. And that value is passed to here. So they can have the same name. They don't have to have the same name. It's called positional arguments, meaning whatever is first here is passed into this one. The value gets passed. So it's like we take the value from this variable and assign it to this variable. So they're two separate variables. We could name it the same thing, but I named it. It shouldn't be plain text. Well, it's plain text in that how we look at hashing as we start with plain text, even if it's bytes, we take those bytes and scramble them. So there's different levels of hashing. So MD5 is like ancient beyond belief. It's like one of the first ones that we ever did. And SHA-1 is like, was starting a new way of doing it. SHA-244 is still deprecated, you know, as the numbers get bigger. That means that more bytes are used to scramble it, generally. We'll see what that looks like in a second. So this is the current one. Oh, yeah, it says most commonly. Oops, did this. Most commonly used cryptographic hash today. So for example, I am signed into my Blackboard. And if I go into here and look at the connection secured, more information, look at there it is. SHA-256 is part of that exchange of information. My password is never passed in plain text. A hash of my password is passed over. My hash word already is stored at Blackboard as a hash. Plain text passwords are not stored anywhere other than on your computer if you have saved it. And even then with Windows, it's in a credential manager that you can't get it out of. There are, like, you can go into your browser and get things out. But if you're making like a remote connection or a network connection, yeah, not so much. So that's used as part of the authentication process, which we looked at that in cybersecurity. We're going to look at that here because how do people get into networks? They break these things so they can capture the packets in plain text. Then they can see whatever you're sending. That's why we use Vuln Web for many of our labs, is that shows what you can do if you can get the plain text. Well, getting plain text out of an encrypted stream with SHA-256 is not easy. So we kind of demonstrate both sides of it, that how you get that unencrypted packet is a little bit more than I know how to do. So 256, 384, 512, each of these has a bigger hash, and we'll see that in a minute. So I'm creating all these hash. We take our hash library, pull out our algorithm, apply it to this. Hex Digest returns it as a string of hexadecimal digits, which is one way to represent binary. On a computer, we typically represent zeros and ones, not as zeros and ones, but we represent it as hexadecimal digits. And what this is doing is digesting this. Oh, there it was. It actually said what it does. It returns the digest value, whatever this is, whatever these BARTs are. It puts it together as a string of hexadecimal digits so you can see it. Because I guess it actually is zeros and ones. I can't remember. So this digests it and says, oh, let's return this as a string. Because it's coming across after it's been hashed up as a hexadecimal, because computers like hexadecimal. Everything is done in hex. All right, so let's run this puppy. I'm going to hash Andy. You feel it there? Oh, there you are. So you can see the hash gets longer with each iteration, which means two things. One is good. That's the balancing act of cybersecurity. There's two major reasons to lengthen a hash. I mean, there's one major reason to lengthen a hash. There's another consequence of lengthening a hash. There we go. So what would be the advantage of having higher numbers in your hash?
Right.
Yep. On the other hand, all this takes computational power.
Mhm.
So the other side of it is, if it takes more computational power, it's gonna take more resources. So security is always a balance between security and what we can afford to do. But over time, as SHA 256 and some encryption suites, let's call it an encryption suite because, oh, where'd my browser go? I lost my window. Okay, I'm gonna have to bring it up again. It's an encryption suite because we don't just use one protocol. Look at all these things in here. AES 124, RSA, TLS. You know, we have 128-bit keys. We're using TLS 1.2. Yeah, all these are great acronyms, aren't they? So SHA 256 is part of the handshaking and saying, oh, does your hash match my hash? Because we can't reverse engineer the hash, but we can compare hashes because these are, what are these? These are strings. Can we compare strings? Oh, yeah. Which is what we're going to do next. Because this is how you hash. This is what a hash looks like. Now we compare strings. This might be the next one. Oh, yeah, this is the next one. Oh, this is something where I got really carried away in my commenting. So instead of having a user input something, I made this into like a little test program to see if you can authenticate to this. We're pretending this is your password. Well, your password is never going to be stored on a server in plain text. What's going to be stored is the hash, but we encode it, and there's our example password. Okay, so our example password is now in bytes for hexadecimal representation. So then I enter what I think is the password. We encode that into bytes. Then we're using SHA 256 because it is the current standard that most people use. That's like the baseline. If you use any lower than that, you're in trouble. You shouldn't be using it. All the rest are what are called deprecated, meaning they still work, but you're advised not to use it. Deprecated also means in operating systems and stuff, that is a feature that's going to be eventually removed. So when they deprecate something in Python, that means you better watch out because at some point they're going to take it out. Well, the hashing algorithms are already out there, so they can't really stop you from using them. You know, they can't take the feature out. They just are saying you should not use that. So we take our example password, our input password, we're going to compare the hashes because the first thing we do is hash each one of them. So there is my example binary hash, my example, I should have said example. Yeah, anyway, I didn't. So these are binary hashes coming in. We do the hex digest thing to make them into something we can compare. So now they're hexadecimal representations, right? We show the example, we show the input password just for demonstration. Normally, you're not going to print the password. And then we say if they don't match or not, which is just a simple matter of doing comparison. Do the hashes match because they are a string at this point. And in Python, we can easily compare strings. So here we go. What's my password? Sean is my is that right? WN? You're a WN, okay. Not like Sean the sheep with a U. There. Here's the example password. Here's your password. Notice the hashes are not the same. So when they're compared, they do not match. You don't usually see all this, but this is part of what's going on in the background when you authenticate to anything. Any place you authenticate, there's a hash algorithm doing this. So how many times a day are you using hashing? Oh my gosh. How many systems do you log into? When do you turn on your phone? When you log into your phone, everywhere you authenticate to anything, hashes are used as part of that password testing. Because we do not want to send passwords in plain text. Do you have to specifically use a hashing algorithm? No, but this is what's going on in the background. This is part of the encryption suite. We don't use hashing specifically, but if we're logging into something, it's being used by the encryption. So we're not using SHA 256. It's being used as part of all the different things we need to do to create a secure connection. It's one of the pieces. Like RSA, for example, that's how we exchange information to negotiate with Amazon. We exchange keys because you don't have a shared key with Amazon. They haven't said, oh, by the way, the shared key for today is password, like you do with an access point. Yeah, that doesn't happen. You negotiate that on the fly. This is part of the encryption, the scrambling suite that can be reversed. It's designed to do that. Advanced encryption something. This is transport layer protocol, which means that instead of at the secure socket layer, which is up here, this is now doing it at the transport layer, which is layer 4. So it's closer to the ground. It doesn't have to go up as far, and it's a better security because it takes the packet as it's being taken apart and encrypts each little packet at the transport layer. I don't know if I'm explaining that quite right. It's more secure than SSL because SSL operates at the application layer. 128-bit keys means that the keys we're exchanging are 128 bits. So we have all this stuff working in here. So you might see some places AES 256. You might say 256-bit keys. Almost everybody uses TLS 1.2 and above because anything lower like TLS 1.1, 1.0, SSL is deprecated because it's been hacked to death. If the protocol still is alive, nobody can take it away, but you're not supposed to use it. So deprecated has two different, one meaning is that don't use it anymore. And like with a programming language, they take it away. Or if an operating system, they take it away. Okay, let's pause for a second because I can't remember if there's anything else here. Boy, we have